Okay, so today we're going to try to work this problem. We want to determine the slope and displacement at point B. That's pretty common in a cantilever system. Probably the displacement at B is going to be the maximum displacement, and the slope will probably be pretty close to the most important slope. So that's going to be good. Now, let's talk about this in terms of what we've covered so far in class. Could I work this problem using direct integration? Before you say yes or no, remember the advantage of direct integration is you get an equation, which you can evaluate anywhere. And it's really nice if you can write a continuous equation for the moment across the beam. So you integrate it once. And in this case, the answer is yes, you can do that. So this would be a good candidate for direct integration. What about conjugate beam? Well, constructing the conjugate beam would not be that difficult, right? The fixed end would become free, and the free end would become fixed. So it looks like the beam just kind of swaps in. But what would the moment look like? Well, this is a constant load, so the shear would be linear, and the moment would be parabolic. Now that could cause you some trouble applying that as load, a parabolic load, onto the conjugate beam, and then finding reactions. But maybe not. The parabola may be well behaved and one that you would know. So this is a possibility for all the techniques. But today we'll try virtual work. Now, virtual work does share something with direct integration in that to start virtual work, what do I have to do? Also write an equation for moment. Right? So I'm going to do that. So can I write a single moment equation for the real loading that's valid for the whole structure? Answer is yes, right? If I cut it, I can cut it anywhere I want, and you see the load is continuous. So if I cut it, do you want to work the left side or the right side? Is anybody, am I here by myself today?
Left side.
Left. Who said left? Why?
Well,
what do I? That's fine. We can do the left side, but what do I have to do if I want to work the left side? I got to find reactions, shear and moment. What if I work the right side? I don't have to find any reactions. So I'm going to work the right side. Save myself some time.
Can you read the forces? It's kind of hard to see. Is that
Can I?
400?
Oh, that's a very good question. It is very small. It is 400 newtons. Trying to see if I can. Did that make it better? Oh, that made it a little better, isn't it? This light is difficult to adjust just right. All right, so what I'm going to do first is I'm going to come over here and I'm going to cut the structure. And I'm going to work the right-hand side so that at some distance x, I will know that segment, my right segment, will be 3 minus x. Okay? So I'll redraw that free body diagram. I have a portion of the load. We have a uniform load that has an intensity of 300 newtons per meter. Also in the very end, I almost forgot it, there's the kind of invisible 400 newton load. And then at the cut, I will assume positive bending moment. And I'll go ahead and redraw that up to this point on the cut is an arbitrary distance x. And that leaves the right-hand segment at the length, which is 3 minus x. So what I need to do is convert the load to a concentrated equivalent. I'll call that F, and it'll be a distance d from the cut. So what is F? Well, F will be the area under this. Let's see if that's a little better. It'll be the area under this part of the loading curve. It's a rectangle, so it'll be the base times the height. The height is 300 newtons per meter, and it's times 3 minus x. So the force will just be 300 times 3 minus x, and that should be in newtons. And what's the distance to the cut? Or the centroid by equivalent force from the cut? Well, whatever, half the distance will be 3 minus x, that's the distance, divided by 2. So now, if I sum moments at the cut and put it in equilibrium, what do I have? Well, my internal moment that I assumed here, my bending moment, with this sign convention comes out to be negative. The equivalent force here, F, what kind of moment does it create about the cut? Positive or negative?
Negative.
Negative. So that'll be negative. We know the force, it's 300 3 minus x times the distance, which we know is 3 minus x divided by 2. And then don't forget our little 400 Newton force. What's its distance? 3 minus x. And it's also negative. So it'd be minus 400, and again, 3 minus x. So solve for the moment, and what do we get? Well, I'll let that 1/2 go over here, so I'll get minus 150 times 3 minus x squared minus 400 times 3 minus x. So there's my moment expression. Is it valid? Do I know the moment anywhere in this system? By inspection? What's the moment at the free end? 0. So that means that x equal 3 meters, I should get 0. If I plug in x equal 3, I do get 0. Now, we didn't find the reactions, but if we did, and we had them in our hand, we could also check that at x equals 0, put an x equals 0 here, then you see you get a big negative moment. That makes sense that it's negative. I don't know if that value is correct, but it looks reasonable. So that's the real moment. What's the virtual moment? What do we want to find? Let's start with the virtual load. So we're going to have the same geometry. And where do I put my virtual load? Well, I want to know the displacement at B. So where's B? It's free end. So I'll put my virtual load at the free end. Remember, now I'm putting it there because that's where I want the displacement. I'm assuming it goes down, so if I get a positive result, it does go down.
The virtual load doesn't have a unit, right?
No unit. Yes, no unit. So now if you look at this one, you'll notice right off that I can do the same strategy I did before. I can make a cut. I can look at the right side at a distance x. Then this little segment part would also be 3 minus x. So I'll come over here and do the same thing I did before. I'll draw a little section, free body diagram. I know that it's a distance x to the cut, and that leaves the length of my little segment to be 3 minus x. I've got my virtual load here, and we are going to assume positive virtual moment. So uppercase for real, lowercase for virtual. And we'll do the same thing we did previously. We'll sum moments at the cut. This is a easier system to do than the real system. First, the virtual moment is negative. the virtual load is creating negative moment about the cut. The load is 1, and what's the distance? 3 minus x. So it looks like the virtual moment here is just equal to minus 3 minus x. And that looks correct too. The moment at the free end is still 0, and it predicts that. At x equals 3, you get 0. And the maximum would be at x equals, I said 0, but I mean x equals 3, the moment is 0. At x equals 0, what's the moment? According to this, it would be negative 3. And I think you can see that's easy to verify. The reaction moment here would be in response to 1 at a moment arm of 3. So that looks reasonable. So what do I have to do? Multiply these together and integrate, right? So now my displacement at B is going to be 1 over EI. EI in this case is constant. And I'm just going to integrate along the length, which is from 0 to 3, the real moment times the virtual moment. So there is the real moment, then there's the virtual moment. I'll just let that negative sign go out here to the front, and I'll have another 3 minus x. Done. There's your virtual work expression for this. Now you see it will take a little time to go through this because you're going to have to expand this. You'll get a x squared, and then of course you'll have to expand it again. So it will get a little messy and quite tedious to do all that algebra. But if you did, you'd end up with an equation that was cubic, and of course you can integrate a cubic polynomial pretty easily. And then the evaluation is pretty straightforward. But for me, probably on the exam, you could just leave it like this. It's good enough for me. You'll notice too that this minus sign would pass through and create this positive and this positive. So now all the terms look like they're more positive. I have a feeling we'll get a positive result. So what I'll do is, just so you can see the final answer if you choose, I won't waste time today in class. I'll sit down in the office and I'll expand this and do the integration, and I'll use the bottom of the page to fill in the result. What I wanted to do next was the second part of the problem, which is the slope. Right? So in that case, I now apply a virtual moment. So in that case, we have the same geometry as before, cantilever beam. I want the slope at B. Here's point B. So I'm going to now apply a virtual couple to the end of the beam. And I'm going to apply it in this direction. And remember, the force unit is 0, and we're assuming that it is a moment, so it's got this weird unit of 1 foot. Now, how would this beam bend with this virtual moment? It's probably going to bend like this, right? And that's positive slope. So if we get a positive answer, we get positive slope. If we get a negative answer, it's going to be negative slope. Just like we did before, to match the real moment, I'll make a cut, and we'll work the right-hand side. Remember that it's at some distance x, and that will leave us a little segment on the right of 3 minus x.
And
Yeah.
I'm confused. What are you doing now versus what you were doing
Well, before I had a virtual force, right? And a virtual force, when you apply it to the system, gives you displacement. So now I'm applying a virtual moment, which is going to give me slope. Right? Force goes through displacement. Moment goes through, it rotates. That's one way to remember which one it is. So the real moment is unchanged. We're going to use the real moment again, except we're going to multiply it times the virtual moment due to the couple. And that will give us slope. Sure. So we'll do the same thing we did before. I'll make a little cut at some distance x. Of course, that little segment is 3 minus x. And what we have on the end is a little couple, a virtual couple. And then what do we have in reaction to that is an internal moment. And we use the subscript theta to distinguish between one caused by a rotation and one caused by a force. Once we've done that, we just proceed as before. We'll do the equilibrium of the system. So I'll sum moments about the cut, make sure it's in equilibrium, 0. So let's see what we've got here. So my internal moment with my sign convention is positive or negative? Negative. And the applied moment is positive or negative? That's it. So what's the virtual moment? 1.
How did your couple you're putting on the end, is that like, you do that every time you try to find?
You put it at the location you want to know the slope, and you assume a direction.
No matter like the load distribution on any type of beam, that's what you do every time. Okay.
Remember, the virtual system is only the virtual load or the virtual couple applied, right? We don't care anything about, the real stuff is taken care of here.
Do you always make it a positive?
You don't have to. I like to use right-hand rule because with right-hand rule, it's always going to rotate like this, and of course that gives me a positive slope. Now, I chose down here.
Yeah.
That's negative displacement. So I probably should have chosen up, because then up would have been positive. If I get a negative value, it would have been negative. But in this case, I chose down, so I think I'm going to get a positive result here, which means I chose the right direction. It's not positive displacement. It's positive because it's agreeing with the direction I chose. The same thing's going to happen here. I'm assuming it's going to be positive displacement. You're going to find out it's not. It's going to be negative. Because the beam probably is going to bend like this. The tip's going to be going this direction. That's negative. So we're going to actually get a negative value here, probably. Somebody else have a question? I saw a hand.
You add in the reactions if there was reactions? Like if we had a...
No, because there's nothing on this segment, right?
What if there were reactions? Did you have to add them in too? Or just
It's virtual. The only thing on the virtual system is the virtual energy that you're putting on it. So if you want slope, you put a virtual couple. If you want displacement, you put a virtual force. Nothing else is on the system.
So is it always going to equal 1?
Yeah. Remember, it's the unit load method, the dummy load method.
I mean,
No. That's just the way it came out for this cantilever. It would not necessarily do that for another application. So no, it won't always equal 1. I think we did a problem previously with the slope, and it was different. I think we were looking for the slope somewhere in the middle. So we had an equation for the slope on the left side, a different equation for the slope on the right-hand side. And they were functions of x. It's just the cantilever. This is a pretty simple problem. What were you going to say, Mr. Kirby?
I was going to ask, like, in what cases would it not equal 1?
Any other case but a cantilever at the end.
Yeah.
Pretty much, yeah. Because if I wanted the slope somewhere else, like if I wanted the slope in the middle of this beam, well, I apply the couple here, right? Well, I'd have one equation that's valid for this section, and then a different equation that's over here.
Okay.
The one to the right would be no moment, 0. the one to the left would still be 1, but that's just because it's a cantilever. Cantilever is unique that way. But if it was a simple supported beam, it would not be 1. It would be something else. Because that moment would induce some reactions, and the reactions would be different on either side, possibly. So all I have to do now is just put these two things together. So I now know the slope at B is equal to 1 over EI. Bless you. Except now we're integrating over the length, but we're integrating the real times the virtual. So I'll just write that out again. Negative 150, 3 minus x squared minus 400, 3 minus x. So that's the real. And then what's the virtual? 1. With that negative sign in front, you can see this is going to come out to be a negative quantity, which is what we kind of picked out before. So I'll do the same thing for right now. I'll just leave this like this. And that's all you'll see on the video if you look at it. But if you look at the printouts of these, I'll go back to the office and complete the integration, just show you what the numbers turn out to be. We don't have a value for E and I, it's constant. So you'll just get a relatively large numerator value divided by EI would be the solution. So any other questions?
Is this the easier method of those?
I don't know if I was asked to do this problem, I would more than likely use direct integration. Because there's my moment equation, right? And you just have to integrate it twice. And when you integrate it twice, you have displacement. Now, you'd have to do a little work to expand that, to do the integration. But remember, when you integrate it twice, you generate two integration constants. And this is the simplest problem in the world for that, because we know the displacement at x equals 0 is 0, and we know the slope at x equals 0 is 0. So both the integration constants are going to be 0. And then all I have to do is plug in x equals 3, and I have my displacement. And of course, along the way, you get the slope equation, right? You integrate the moment, you get slope. Integrate the slope, you get displacement. And I just go back to my slope equation and evaluate it at 3, and there's the slope. So I would probably choose direct integration. I'd probably go direct integration, virtual work, conjugate beam, dead last. I'd put that one off. This would not be a good conjugate beam problem. Now, if the distributed load was gone, it'd be a great conjugate beam problem.
So on the test, are you going to ask us, are we going to be able to choose what method we use?
Yeah, I'll give you a problem just like that. It doesn't say use any method. It just says determine the displacement or determine the slope at this point. You choose. Which is harder work for me because I have to work every problem every possible way I can think of. Where you get to pick one way. But in a class like this, somebody will pick direct integration. So I have to have a direct integration solution. Somebody will pick virtual work. Somebody will try conjugate beams. It's inevitable. So I think it's part of this is for you to really use the most efficient method, the best tool for the job. They'll all work, but they'll eat up your resources. So you want to use the one that you're the most comfortable with, and that efficiency is the key.
So how do we know which one to use? Like, I started doing some conjugate beam, but then I realized it's hard. So I went back to different way. So how do you know just by looking at like, oh yeah.
Well, I'm going to say that if you have a continuous load, direct integration and virtual work are your friends. If it's not continuous, then you have to look at it carefully. Virtual work is going to be the same every time. You can see it. This much effort. It's pretty much the same. If you want to put all your money in one method and not even worry about the other ones, I would probably say virtual work is the most the best tool. However, there are problems where direct integration would be better. There's a class of problems where conjugate beam would be better.
So even if we choose a different method, are the answers to the question going to be the same?
Oh yeah, right? There's the deflection of that beam or that load. Is it going to change if you choose a different method? Well, your answer may be different, but the deflection of that beam at that point is some value. And all those methods should get to that value. Should. Like you all should get the same answer on every problem. Do you all get the same answer on every problem? Not that I've seen. Okay. We'll stop that. That went longer.